Have you ever just stopped and thought about all the invisible things that keep our world running? I mean, from the thermostat in your house to the crazy complex machines that build our phones, there's this hidden layer of intelligence just quietly keeping everything in order. So today, we're going to pull back that curtain. All right, let's get into it. So yeah, how does it all work? How does your world, your car, your house, stay perfectly in balance when the outside world is constantly trying to throw it off? Well, it's not magic, that's for sure. It's engineering, and it's a concept that is just so elegant and so powerful. I mean, think about your home thermostat, right? You set it to a perfect 70 degrees, and whether it's boiling hot outside or freezing cold, your house just kind of stays there. That's our first big clue. Or what about cruise control? You tap a button, and boom, your car holds a rock-steady 65 miles an hour. Doesn't matter if you're going up a hill or down one. It's making these tiny, constant adjustments to the engine, way faster and more precise than you ever could with your foot. And this stuff goes way, way beyond our personal convenience. You look inside a modern factory, and you've got these robotic arms assembling our gadgets with just incredible speed and precision. They can do thousands of these exact, repetitive movements and never get tired, never make a mistake. And you know what? All of these things are powered by the exact same fundamental principle. And that principle, the big idea for today, is called a control system. At its heart, a control system does three simple things. It measures something, it compares that measurement to a goal you've set, and then it takes action to get rid of any difference between the two. That's it. Measure, compare, correct. That's the loop that basically runs our modern world. Okay, so to really get this, we gotta learn the language. Let's stick with an example we all know and love, the air conditioning in your car. We're gonna use it to break down the 4 key terms you absolutely need to know. First up, we have the plant. Now, in control engineering, this has nothing to do with something green that grows in your garden. The plant is just the physical thing or process we're trying to control. So in our car example, the plant is the passenger cabin. That's the space we want to keep comfortable. Okay, next, what specific thing about the plant are we trying to manage? That, my friends, is the controlled variable. For our car's AC, it's pretty obvious, right? It's the air temperature. That's the one thing the system is constantly measuring. Now here's the thing. Nothing ever exists in a perfect little bubble. There are always outside forces trying to mess with our plan. In this world, we call those a disturbance. For our car cabin, the big disturbance, the main enemy, is the sun just beating down on the roof or the hot air outside. That's what the control system is built to fight. So, how does our system fight back against that enemy, the sun? It uses what's called the manipulated variable. This is its weapon. For our car, that weapon is the flow of cold air blasting from the AC vents. The controller can crank that cold air up or dial it back to perfectly cancel out the disturbance and win the battle for that perfect cool temperature. All right, now that we have the lingo down, we can talk about the 2 big philosophies of control. And you can really think of it as a choice between a system that is totally aware of its own results and one that is, well, completely blind. So path number 1 is what we call open loop control. This is our blind controller. It just follows a pre-programmed plan and kind of hopes for the best. A perfect example is a simple washing machine. You set it for a 30-minute cycle, and it's going to run for exactly 30 minutes, period. It has no idea, no clue if the clothes are actually clean at the end. It just follows the timer. So let's put them side by side. On the left, you've got our blind open-loop system. The washing machine runs its timer, and that's that, completely unaware of the actual result. But on the right, you have the aware, closed-loop system. This is your cruise control. It's constantly getting feedback. It's actually measuring the car's speed. So when you hit a hill, a disturbance, it senses the car slowing down and automatically gives the engine more gas to fight back. That's the whole ballgame right there. One is blind to the outcome, the other is literally built to see it and react to it. So you might be thinking, why would anyone ever choose the blind path? Well, it all comes down to a classic trade-off: simplicity versus accuracy. Open-loop systems are dead simple to build, which makes them cheap. And because they're not constantly trying to fix themselves, they don't have stability issues. You use them when the thing you're trying to measure is just really hard or expensive to check. I mean, how would you even build a sensor to measure the cleanliness of clothes, right? But their big weakness, of course, is that they can't adapt. They're totally helpless against anything unexpected. You know, this whole idea of an aware system, It feels super modern, but it isn't new at all. In fact, its history is this amazing journey that basically mirrors our own technological story, from the age of steam all the way to the age of software. It really kicks off back in the 18th century with James Watt's centrifugal governor, an absolutely brilliant mechanical gadget that automatically kept steam engines from running too fast. Then, fast forward to the early 1900s, you have engineers using some serious math to figure out how to make ships steer themselves stably. The 30s and 40s saw huge breakthroughs for things like long-distance phone calls, but the really big shift happened in the 1950s. We went from just trying to build things that worked to trying to design the single best, most optimal system possible. And then, of course, in the 60s, computers came along and just blew the doors off, leading to modern control theory and letting us manage insanely complex things like the Apollo rockets. And that's what we're still doing today, pushing the limits of robust control for everything from fighter jets to factories. But here's where it gets really cool. This logic of measure, compare, correct isn't just for machines. Not at all. It's a fundamental pattern of the universe, something you can see everywhere, from the planet itself all the way down to the cells in your own body. I mean, think about it. Your own body is an incredibly advanced closed-loop control system. It uses all this physiological feedback to keep your temperature and blood pressure constant without you ever thinking about it. A good business uses performance reports, that's feedback, to manage its operations and change course when needed. Economists even use these same ideas to try and manage massive dynamic financial systems. It's like this universal blueprint for keeping things in balance in a world that's always changing. And that brings us to a final, and I think really important question. The power of automatic control is just growing exponentially. We can automate more and more complex, more dynamic, and more critical systems every single day. But just because we can automate something, does it always mean we should? As these systems take over more and more of our world, maybe the most important question we're going to have to answer is deciding what still needs that human touch. What's the one thing we should choose to never, ever put on autopilot?